So far we have seen that it is not easy to obtain low noise figure while making sure the input impedance is also matched. So to be able to obtain noise and power matching together, we may need to try a different approach. So here we'll use an intuition to see if it is possible to get a real impedance without actually using a resistance. So let's say we have a purely imaginary current like this, and we force this current to flow through another impedance which is also purely imaginary, some kind of Jx. And when this happens, we can easily see that the voltage drop V is going to be equal to Ji into Jx. It is of the form minus I into X. So by choosing the X and I appropriately, we can control this polarity. But the takeaway message is, without using actually a real impedance, we can get a voltage drop which is purely real. This is real voltage drop without using real impedance. So this intuition is going to be useful when we are trying to realize impedance for input matching without using resistance. Problem with resistance is it also adds noise. Now let's see where this kind of scenario is possible when we are trying to use MOSFET for amplification. So in a MOSFET, we know this CGS is always present, and because of this CGS, the looking in impedance turns out to be capacitive. Now, if we force a current, let's say Ix, through this CGS, then what happens? The voltage drop across the CGS is going to be equal to Ix divided by j omega CGS. Good thing about this VGS being reactive is that the current which is generated by the MOSFET will also be reactive in nature. So it means this current IDS will equal to VGS is equal to GMIX divided by J omega CGS. Now we have found a way to generate a current which is purely imaginary, and if we can now force this imaginary current to flow through a purely reactance and imaginary impedance, then we can expect that the voltage drop is going to be real. It can be done by, say, adding a reactance on the source side, so that when this current flows, it will cause a drop, and this drop we can expect that going to be having a real component. So when we look from the gate side, we will be encountering some drop across this reactance which is going to be in phase with the light current. As a result, the input impedance will also have a real part. So let's see what is the overall voltage drop we are getting. So let's call it Vx. So this total voltage which is applied, say, as a result of V test. So this V test is equal to Ix, which is flowing through the CGS, divided by J omega CGS, plus the drop across this reactance Jx, which is equal to Ix plus Gm times Ix divided by J omega CGS, which is flowing through this Jx. Okay. Now we can see, if we look at the input impedance, which is V test by Ix, it's going to be equal to 1 by J omega CGS plus Jx plus Gm by J omega CGS into Jx. Here we can cancel this J so as to get these two reactive terms plus Jx and one completely real term. Now we can see that we have found a way to obtain a real impedance without actually using a resistor. And if we want this, looking at impedance, to have a real part, let's say, which has a resistance of Rs, then we can choose the X to be an inductor, and we can choose this quantity to be equal to the Rs. Okay, so this is how we can come up with this circuit where an inductor is connected at the source side. Let's call it Ls, CGS. And to be able to see a purely real input impedance, we can compensate this reactance by adding another reactive component. So many times you'll find that by adding an extra inductance here, we can compensate the reactance of CGS and LS. So if you connect the source Rs here, we call it some extra inductance at the gate Lg. Such a scenario, this MOSFET is biased with a transconductance of Gm, then this Zin, which is equal to now 1 by J omega CGS plus J omega Ls plus Lg plus Gm omega Ls divided by omega CGS. Okay. So omega gets cancelled, and another part is series resonance at omega. So these reactive components will just cancel each other, so that Zin is going to be purely real quantity equal to omega t ls, where omega t, if you remember, is the transit frequency Gm by Cgs. So you can choose the components as that a design frequency. Input impedance is purely real and equal to omega TLS. Another point to note down here is this real part is actually broadband. This real part doesn't depend on the omega. Only this reactive parts depend on omega. Okay. Broadband real impedance. Okay. So this common source amplifier with inductive degeneration is really popular because of this reason. And now we are going to analyze this circuit for gain and noise figure. Inductively degenerated source amplifier. This. Let me redraw the circuit with the load. See, CGS, LS. We have a tuned load here. What I will do is I will just model a resistance R in parallel with the inductor, which will capture all the real impedance looking at the load side. RP, and here there is a CL. This MOSFET is bias band saturation with transconductance GM. This is the output. If you want to find out the gain, we can first find out what is going to be this voltage VGS. So if we know VGS, then we can find out this output voltage. So we know that at design frequency omega, this looking at impedance is RS. Okay, so this is for matching. So it means the current which is flowing in this loop is I. S is going to be equal to Vs by 2 Rs. Okay. Now it makes it very easy to find the voltage across CGS. So voltage across CGS, VGS is going to be Vs by 2 Rs into 1 by j omega CGS. So once we know the current, the voltage VGS, we can find out IDS. So it implies V out, which is going to be equal to minus GM VGS, that is IDS, into RP at the design frequency. The L and C are going to just resonate out. Going to be equal to minus GM RP divided by RS J omega CGS. One thing you will note here is, since it's a series resonance at the input side, so the voltage across this capacitor is going to be Q times the applied voltage. So this VGS is also equal to Q in into Vs, where Q in we can define as the quality factor of the input RLC circuit, which is 1 by omega CGS into 2RS. And of course, this extra J will also come into picture. Okay, so if we simplify, gain VO by Vs becomes minus GMRP into Q in divided by J. This Q in is really important because we can see that because it's series resonance, already the VGS is getting amplified by the quality factor of the input resonance circuit, and this passive amplification is going to generate this IDS and then V0. So this extra passive amplification is going to increase overall gain, and we can also expect it will improve the overall noise figure. So this gain can be pretty high by choosing a high value of GMRP and Q. Now let us try to find out the noise figure of this circuit. So I will just draw the simplified circuit for the inductively degenerated common source amplifier. S, LG, CGS, LS, and on the load side I will just show RP. If we look at the noise sources, so we have noise due to RS, noise due to MOSFET, and then there will be noise due to RP. If you want to find a total output noise, ESD, it is going to be first the noise from the RS multiplied by the transfer function square. It is 4 kT RS. The transfer function is GM RP Q in. Okay, square plus, if we find the transfer function from the IND source, current source to the output, we can find the contribution also. Now this transfer function can be done as we have done earlier for a MOSFET, where you can use two approaches. One approach you can split, repeat. So as we have done earlier, you can split this current source into two current sources in series, and then this middle node can be connected to any node in the circuit. So if you connect to a ground, it will simplify your circuit analysis, and then we can find the contribution due to each of these sources independently and add their contribution at the output finally. So if we do this analysis, you'll find that when matching is present, means when RS is equal to the Zin, so these LG, LS and CGS are in resonance, as well as the looking at impedance as a real part, omega TLS, which is also equal to RS. You'll find that half of this current loops back, whereas half of it is flowing outside. Okay. So the actual current going to the output is going to be only half of this IND. So the transfer function from the IND to the output. So V O due to IND is going to be half of this current going at the output multiplied by the RP, and input is matched. So I'm not showing this derivation. I'm sure all of you will be able to do this. So the noise due to IND, the output will be 4 kT gamma GM multiplied by RP square by 4 plus the noise due to RP, which will come as it is 4 kT RP. So now we should be able to find the noise factor. This is 1 plus 4 kT gamma GM RP square by 4 plus 4 kT RP divided by 4 kT RS to GM RP Q in square. Here already we can see that in the numerator, if you compare these two terms, this is going to be much higher compared to the noise due to the RP because of the extra gain. We can ignore for now. This is going to be 1 plus gamma GM RP square by 4 into 1 by RS GM RP and Qn square. So Qn is 1 by omega CGS to RS. So this entire term is whole square. Noise figure is 1 plus gamma GM RP square by 4 into omega square CGS square 4 RS square divided by RS GM square RP square. Okay, simplify. This becomes equal to 1 plus gamma GM RS into omega square, and again we see this GM by CGS kind of term is coming. So this is the final expression for the noise factor. Now let us see what kind of noise factor value we are getting. If we look at this term, we have this omega by omega t whole square, where omega is the design frequency. The design frequency for our applications can be, so it will be, let's say, omega less than 5-6 gigahertz. And this omega t is the transit frequency. And this transit frequency can be easily more than 100 gigahertz. In a more advanced process, if you see, this omega t will be also touching 200 gigahertz. We can see that under such a scenario, this omega by omega t can be a very small quantity, so that second term can be much smaller than 1. So we can conclude that this f can be much smaller than 2, or noise figure can be much smaller than 3 dB. Just the most technical. This is an important conclusion, that we are able to obtain perfect input matching while making sure the noise figure is less than 3 dB. So we have seen in all the other approaches this was not possible, but a inductively degenerated common source configuration allows noise and power matching to happen at the same time. So key point to note here is noise and power matching is possible simultaneously, and there is a passive gain upfront due to series resonance in the input network. Now the passive gain due to series resonance is also possible in a regular common source amplifier, but you cannot maintain the input matching. And to complete the picture, we need to make sure omega t ls is equal to rs, as well as the series resonance which is happening because of LG, LS, and CGS should take place at the design frequency. to ensure both of these criteria are satisfied. For a practical design, we will see that when we are trying to obtain the input matching, there will also be some CGD present, and the CGD can actually cause instability as well as can make this looking in input impedance dependent on the output network. So what we can do is we can add a cascode element to shield the input from the output. P, RP, and this cascode element can not only improve the input matching, it will also improve the stability of the LNA. You'll find that the noise generated by the cascode will not completely appear at the output because of high degeneration from the input element. So this cascode can actually help in improving the stability and input matching while not degrading the noise figure so much. So the CGD adds feedback path between output and input. In instability. So cascode element improving the stability by input effectively by cutting any feedback path between the output and input.